Greetings to Dr. Azali and fellow audience. Our project title is Design and Evaluation of Data Parallel Application using OpenCL, and the problem scope we choose is Parallel Matrix Operation. This is all the problem that we found, but the main problem we address is the inefficiency of sequential matrix multiplication. Traditional CPU implementation use triple nested loop with this computational complexity, which become a very slow as matrix size increases. This approach also fails to utilize modern parallel hardware such as GPUs, causing inefficient resource usage. This limitation become critical in real-world applications like machine learning, scientific computing, graphic, and data analytics, where large matrices must be processed repeatedly under time constraint. Our motivation is to utilize modern hardware, such as GPU, using OpenCL, which allows data parallel execution across heterogeneous devices. So for high-level architecture, it consists of CPU host for RAM and OpenCL device. The CPU generates input matrices, manages memory, the kernel, and verifies the result. And then the OpenCL devices execute the parallel kernel where each work item computes one element of the output matrix. Next, I will explain our code implementation. So first, we implement the sequential CPU version in Python. Using this function, we generate two 1024 by 1024 matrices. Matrix multiplication on CPU is performed by this function, which uses three nested loops over indices I, J, and K to compute each output element. This sequential implementation is used as our performance baseline. And then, this is where we execute the CPU version and record data execution time. Next, the host code selects an OpenCL devices. This is our OpenCL kernel. Each work item computes one element of the output matrix. The row and column indices are obtained using getGlobalID inside the kernel. We loop over K to compute the dot product. Here we allocate device buffer. Matrices A and B are copied to device memory as read-only buffer, while C is allocated as write-only output. We launch the kernel using a two-dimensional global size of 1024 by 1024, creating over 1 million parallel work items. After the execution, results are copied back to host memory and compared with the CPU output to verify the correctness. So for the live demonstration, we execute both CPU and OpenCL version. First, the CPU performs matrix multiplication sequentially, and the execution time recorded is approximately 494,069.89 milliseconds, which is about 494 seconds or over 8 minutes. And then next, we run OpenCL implementation on the selected device, which is Tesla T4 GPU. The GPU execution time is approximately around 96.85 milliseconds. To verify the correctness, we compare CPU and GPU results using this function with tolerance 1 exponential negative 3. So the result shows GPU result match CPU, which confirm numerical correctness. Finally, we analyze the performance. So the OpenCL implementation is 4,940 times faster than CPU sequential. This is because the GPU execute over 1 million work items concurrently, while the CPU version runs sequentially. The CPU approach is limited by single-thread execution and O(n)(3) complexity. OpenCL maps each matrix element to an independent thread, enabling massive parallelism. However, there are bottlenecks. Our kernel uses only one global memory and does not apply tiling or shared coupled memory, causing redundant memory access. So for future work, we plan to include local memory optimization, work group tiling, and kernel tuning. In conclusion, OpenCL significantly accelerates matrix multiplication while maintaining correctness, demonstrating the effectiveness of data parallel computing. And then that's all from me. Thank you.